right? Or principle of conservation of energy, which is basically our Bernoulli's principle, right? And here we said we had a viscid flow, we ignored losses, and so on and so on and so on. But now we don't want to ignore losses, so we have to account for our shock losses, and we get our shock losses from whether we have an expansion, a contraction, some sort of constriction or flow meter, or we have a bend in the pipeline, or something like this, or a valve, or something, right? Then our frictional loss comes in this problem, this H value, right? And remember, when we're applying Bernoulli's principle, it's a point function, right? So when we're applying the principle of conservation of energy to any problem, you can apply it between any 2 points in the system, right? Here I'm looking at these 2 points, A and B, right? But I can also look at here and here as well, if that's what I wanted to do, and so on and so on, right? You can apply it between any 2 points. So we were applying it between points A and points B. And as you saw before, we need to choose a datum point, right? So it doesn't matter where you choose as your datum. Here we chose A as the datum, where A is at this level. We could have chosen point B or point C, doesn't matter, right? But we chose point A here, and we're applying Bernoulli's principle between points A and B, and then we are accounting for our shock losses, right? And our frictional losses. So we apply Bernoulli's principle between points A and B. So we start off by writing our expression like that, right? Because we're applying it between points A and B. And then we need to identify all the locations where we're going to have our shock losses as well as our frictional losses, right? So, so we did that. We identified that we're going to have a shock loss at this location right here, right, where we're going from a reservoir into a pipeline. So it's basically a contraction. We call it a special case, right? It's a special case. And remember, we said if there's nothing said about that transition, you take it to be negligible or zero. However, in this question, you were told that the entry was sharp, right? You were told that the entry was going to be sharp. And then we're also going to have frictional loss in that pipe section between this point here and B. So we need to add that component as well, right? So these are the two losses that we've identified. Then you can do some elimination, right? So we know that since A and B are open to atmosphere, our pressures there would be zero. So we can eliminate at A, your velocity will also be zero. So you can eliminate some of these expressions, and so you can simplify the expression, right? So we want to find H, which is actually our Z. No, actually, sorry, we want to find the flow rate here. We want to calculate Q, not H, right? So we can see that here our H is really ZA minus ZB, right? Or ZB minus ZA, however you want to look at it, right? And we basically simplify the expression, right? So we end up with VB being the only unknown in that expression. And then we can use VB to find our flow rate in the pipe section, right? Based on our principle of continuity, our AV, Q equal AV, right? Because we found V already, and we can then find the flow rate in that section. It's that simple, right? Any questions on this? questions for me?
Dr. Maloney, the datum in this particular problem, what did we choose our datum to be?
So the datum was chosen as A, as this level here. That's why it's at 0. You can see right here. Right?
Okay, I see. Okay.
So anything, so B would be below that datum. So your ZB would be minus 12, right? Because it's below 0.
Yes.
Right? So if we had chosen B as the datum,
Okay, I see.
then Z would be 12, right?
Yes.
So if we had said ZB was 0,
Mhm.
in this case, your ZA would be 12 meters, right? So, but it doesn't matter. You just have to, once you choose your datum, you stick to convention. If a point is above your datum, it's going to be positive. If it's below, it's negative, and so on, right? So you are free to choose any datum you want. In the end, you should get the same answer, right? It doesn't matter. You just have to be careful and you have to follow the rules, right? Okay, so let's move on, right? So we have another example now, right? And again, I don't want these things to scare you. Once you apply your Bernoulli's principle, you apply the right equations for your shock losses, you shouldn't have a problem. Now, if you go into textbooks and so on, you're going to see a whole lot of other stuff, right? But it's the same thing that the textbook you're going to see that they're doing, we are doing the same thing here. So you might see some slightly different expressions for different types of losses in bands and all sorts of things, in valves, if you have a valve, if you have, and so on, but they're going to be applied in the same way. You should be able to pick up a textbook and understand exactly what they're doing, right? Quite easily. So here we want to also find the flow rate. Let me see, let me make sure. No, we want to find H, right? We want to find H. We have been given the flow rate, right? So we want to find this H value here, right? Which is actually ZA minus ZD. We want to find the head, right? So again, I am going to apply Bernoulli's principle between points A and points D, right? D being where your flow is being discharged to atmosphere, right? So A is the top of the reservoir. D is where the discharge is taking place, right? And then I'm going to add all of my losses, right? So you can see I have a loss at B, a loss at C, right? There's 2 shock losses there, right? And then there's frictional loss between these 2 sections, between section B and C, and between sections C and D. So I have 4 losses. I have 2 shock losses, 2 frictional losses, right? So now I can add this is my shock loss at B right here, this one, right? Or D, right? Or B, sorry, where at this point. Then I have my shock loss at C now, right? That's the frictional loss, that 4FL and D, right? Then I have another shock, and then I have another frictional loss, right? And I want to simplify all of this now, okay? So I eliminate as before. You can see where I'm eliminating, right? And then I'm putting in values for that have been given, right? So I can find my I can use Q, sorry, right, to find pi d1 squared on 4 v1, right? Q is also equal to pi d2 squared on 4 v2, right? So I can find the velocities in the different sections, right? Because I have the Q, I know what Q is. So I can find V1, I can find V2, right? Using the continuity principle. And then I can plug that in to give me my ZA minus ZD, right? So I hope you're getting the idea here. We always almost need our continuity principle in conjunction, right? We're using the principle of conservation of mass as well as the principle of conservation of energy, because sometimes we have more than one unknown, and we will need more than one set of equation to help us to solve for what we're trying to get in, we're trying to figure out, right? So if you find yourself running into problems, more than likely you're not using the continuity principle, or you need to use it to help you to get out of a jam, right? And you'll see how it comes in handy later on when we start looking at branching systems that are branching. Any questions here on this one?
Dr. Maloney, so I'm trying to see how like you rearrange the equation. So you're given all the like the variables. I see where it's H equals ZA minus ZD.
Yeah, and that's what we're trying to find. We are
Yeah.
trying to find H, right?
Yes. And then so you're giving all the variables to the right side of it. And
No,
but you
I'm not given all of them. Some of them,
which is why you have to use the continuity.
correct. So
Okay.
I'm not given the velocities,
Okay, that makes sense.
right? I'm not
Yeah.
given V1 and V2, right? And if you
Mhm.
notice, I'm calling V1 the velocity in the first section of pipe, and V2 the velocity in the second section, because you know
Okay.
that if you have a change of section, the velocity is going to change,
Yes.
right?
Mhm.
So, so I'm calling it V1 and V2. And you can find those by using the continuity principle, because you have the flow rate. The flow rate was given to you. And you
Mhm.
know that Q is equal to A1 V1. It's also going to be equal to A2 V2. And you have the diameters of those sections, so you can find the velocities of V1 and V2
Okay. Thank you.
that you can then plug into this equation, right? Because you have everything else. You have L, we've given you L1, we've given you L2, you have D1, D2, you have F1 and F2. And once you find the velocities, then you don't have any other unknowns. You can plug that all in and you can find your ZA minus ZD. Right?
Yes.
And again, don't watch me do this. Go practice. Go do the problems, right? I mean, it's good enough for me to set up these equations, but the only how you start getting the feel for working these things is to actually do problems, right? Okay. So let's look at another one. This time I want to look at what we want to look at branches, right? Parallel pipes and branching lines, right? And you see how we do that, right? So here I have two reservoirs, right? Reservoir A, reservoir B, right? And I have three pipes that are parallel to each other. Now, I want to make something clear. It does not necessarily mean that these lines are actually parallel. All it simply means, right, is that they're going technically between two reservoirs, right? These lines could actually be doing something like this, right? But we still call them parallel, right? Technically, right? Because the head, right, between between all of these pipes are going to be the same. So you see I have H drawn here, right? So we are going to essentially say my head, and I'm taking my head as the difference in levels between the two reservoirs, my A and my B, right? So what these three pipes are going to have in common is that H is going to be basically the same for all of these pipes, right? That's what these pipes have in common. So we're going to set up Bernoulli's principle, right? And remember, we are setting up Bernoulli's principle, right? Between points, between 2 points, right? So I can say, okay, I'm going to look at this first pipe here. I apply Bernoulli's principle to that pipe. I apply Bernoulli's principle to this second pipe. And I can also apply Bernoulli's principle to this third pipe. Now, these three pipes, their diameters are different, right? The first pipe has a diameter of D, the second pipe has a diameter of twice times the first one, and then the third pipe has a diameter of 3 times the first one, right? But the thing that these pipes have in common is that they are running between the same reservoir. So my H value for these pipes are going to be the same, right? But my Z, if you want to say my ZA minus ZB, so if you want to say that H is equal to your ZA minus ZB, that's going to be the same for all of these pipes, for each one of these pipes. Now, remember, so I'm going to set up my Bernoulli's principle again, right? You can see here, right, between A and B, and then I only have frictional loss because the problem doesn't tell me anything about the this section where I enter and where I leave the pipe, right? So you can ignore those losses at entry, exit and entry from the reservoir. So you see I have a note here, right? So the only loss that we need to consider is the frictional loss in the pipe, in these pipes, right? So now we can then simplify. You know that at PA and PB, that's open to atmosphere. My VA is going to be 0 because it's starting at the reservoir, same as VB as well. That's also going to be 0. If you look at the surface of a reservoir, it doesn't really move, right? That's basically what you're saying. So my ZA minus ZB is just going to be equal to the frictional loss inside of that pipe, right? Because that's the only loss I'm considering. Now remember, early on, I can write my loss equation in this form. So there are 2 forms I can write my equation in, and I'll go back and I'll show you because I'm sure most of you have already forgotten. So I'll go back and I'll show you where I introduce this, right? And it's right here, right? So I can write my frictional loss inside of a pipe either in this format or in this format, right? Your FLQ squared on 3d to the 5th, right? Or we can write it on this, in this format. Now, we're using this format here because it's very useful, because the problem gave you the value, I think it told you what the flow rate was, which you have here. It gave you the flow rate, right? So the flow is basically going to be the same. I think that Q1 is the flow in the smallest pipe, just the smallest pipe, right? But you know that H is going to be the same for all these pipes because they are running between the 2 reservoirs. So now we can write our ZA minus ZB, right, in terms of that FLQ squared on 3D to the power of 5, right? And we can write that for the pipe 1, pipe 2, pipe 3. This is pipe 1 here. This is the second pipe, third pipe, because H is going to be the same for all of them, right? Going to be the same. So I can say FL1 Q1 squared on 3D1 to the power of 5th, and I do that for the second pipe and the third pipe as well. The problem also tells me, right, that F is the same for all pipes. L is the same for all the pipes, right? So I can eliminate that F and L and the 3 in the denominator. So I basically end up with an expression that is like this, right? And I also know the relationship between the diameters of all the pipes, right? So, and I have the flow rate in the smallest pipe, right? So I have enough information basically to find the flow rates in the second pipe and the third pipe, because that's what the question wants me to do. It wants me to find out what is the discharge, right, in the two larger pipes, in Q2, in D2 and D3, pipe 2 and pipe 3, right? So I take the first two pipes, just D1 and D2, and I substitute for D1 for D2, because I know that D2 is twice times D1. This is D1, right? So I end up with an expression, right, where Q1 or Q2 squared is equal to 32 times Q1 squared. And I can simplify that. Q2 is equal to the square root of 32, but times Q1. And I know what Q1 is. So basically, I can calculate Q2. And then I do the same thing again for pipes number 1 and 3. Same thing. And I get an expression, right, for Q3 is square root of 243 times Q1, right? So that's how we use this information, guys. We're just using all the knowledge we have to solve these problems, right? To work towards what we need, right? So sometimes you need to recognize that this form of your frictional loss, you can represent it in that form, right? Where you have FLQ squared on 3D to the 5th, right? Which is also 4FL on dV squared on 2G, right? So sometimes, and that's our HF or H frictional, right? So keep that handy. I will give you these formulas, but you need to recognize that sometimes you may need to, depending on the information you have, you need to use the formula in this form, right? As opposed to this form here. Questions on this?
Dr. Maloney, I have a question on this one too. So I see how you equated the discharge for all three pipes because they have the same H.
Yes.
But I guess it's what I'm not understanding is like they all three have different diameters. So how will they have the same discharge? But that shouldn't matter since they have the same
They
H.
don't have the same discharge.
Okay.
So if you let's read the question. It says two reservoirs are connected by 3 pipes in parallel. And I want to clarify, parallel doesn't mean that they are actually parallel. It simply means that they're running between the same 2 reservoirs, right? And you've been given the diameters D1, D2, D3. So we have the diameters of each pipe. which, and they told us, right, that the diameter of the second pipe is twice times the diameter of the first pipe,
Mm-hmm.
and the diameter of the third pipe is 3 times the diameter of the first pipe,
Mm-hmm.
right? And then they also told us that all of the pipes are the same length, L. They said assuming F, which is the frictional coefficient, right,
Mm-hmm.
to be the same for all pipes. And then they say what will be the discharge through the larger pipes if that through the smallest is 0.03 meter cube per second.
Oh, okay.
They said the smallest pipe, they told us what Q1 is, if you want to call it Q1,
Mm-hmm.
right? The smallest pipe, 0.03 meter cube per second. But they want us to find Q2 and Q3. We don't know what the flow is. We can't assume they'll be the same. They'll be the same, and they're not, because they're bigger pipes,
Yeah.
right? They're not, right? So that's how we start, right?
Mm-hmm.
I don't know. Have I answered your question or no?
The first box on top that H equals Q1 squared equals Q2 squared, like the whole the three ratios. So so you focused on the discharge for the first and second one because you want to find the second discharge, and you're given the first discharge.
Yes, because they're all equal. So the head loss
Mm-hmm.
for
Okay.
each pipe is the same,
Mm-hmm.
right?
Mm-hmm.
Because they're all running each pipe. Each one of these pipes are running between the same two reservoirs. So H for these 3 pipes would be the same for each
Yes.
one, right?
Yeah.
But the problem gives me flow rate and diameter. I know what the flow rates are
Mm-hmm.
for the first pipe, and I know what the relationship diameters for each pipe, right?
Yeah.
So that's why, and let me go back to here, right? So that's why, remember we said my H is ZA minus ZB. But we worked out Bernoulli's principle, and we saw that we can eliminate everything else, and then we end up with this 4FL on dV squared on 2G, right? Which we can also write as our, let me go back here, as this FL Q squared.
Yes. Over 3D to the power 5.
3D to the 5th.
Mm-hmm.
Right?
Mm-hmm.
But remember, we said that our H1 is equal to H2 for each pipe.
Yes.
Right? Which means I can write F1 L1 over Q1 squared on 3D1. That's the first pipe.
Mm-hmm.
F2 L2 Q2 squared 3D 2 to the 5th. F3 L3 Q3 squared over 3D 3 to the 5th.
Mm-hmm.
Then I can eliminate these guys, because the question says all the F's are the same, all the pipes, the lengths are the same.
And they cancel out.
We can eliminate trees as well.
Mm-hmm. And they give you the diameters, and you substitute that.
Right. So now I have Q1 squared over D1 to the 5th is equal to Q2 squared over D2 to the 5th, Q3 squared over D3 to the fifth. So all I have now is a relationship between diameter and flow rate.
Okay. See, okay, that's where I assumed wrong. I'm assuming that the discharge is all the same since
The
it's like,
charges are not the same.
yeah, it's not.
No.
That's based on the H, where they have
Right.
the same. Okay.
And then I can then say, okay, let me just take these two then together. Because I know what Q1 is.
Mm-hmm.
And I know that D1, D2 is equal to twice time D1.
Yeah.
Right?
Nice. Mm-hmm.
So I can then say, okay, Q1 over D1 to the fifth is equal to Q2 squared over twice time D1 to the fifth.
Mhm.
Right?
Yeah.
So I get Q1 squared over D1 to the fifth. Let me take it to another page. Let me add, let me just add a page here. Right, so I can say, let me just rewrite it here. So Q1 squared over D1 to the fifth is equal to Q2 squared over D2 to the fifth. And I know that D1 is equal, sorry, D2 is twice time D1. So Q1 squared over D1 to the fifth is equal to Q2 squared over twice time D1 all to the fifth. Q1 squared over D1 to the fifth is equal to Q2 squared. 2 to the power of 5 is 32. D1 to the fifth, right? So then I can eliminate D1s.
Yes.
Those. So then I have Q2 squared is equal to 32 Q1 squared.
Mm-hmm.
But I know what Q1 is. The problem said that
Yeah.
Q1 was 0.003 or something like that.
Mm-hmm.
So now I can do Q2 is square root of 32 Q1. I know what Q1 is.
Mm-hmm.
So I plugged it there and then I have Q2. And I do the same thing. I go back and I do the same thing now between Q1 and Q3. Or if you want, now that you know Q2, you can do it between Q2 and Q3.
Yeah. Okay. Thank you, Dr. Maloney.
Right? So that's, again, guys, it's one thing to look at me practice both these problems, but you have to work them. That's how you're going to get the feel for it. You have to do these problems. There's no shortcut here to this, right? You have to just jump in and do the problems, right? So that's one. Again, this is a unique problem because we're looking at we're applying Bernoulli's principle between two reservoirs, and the understanding here is that your head, your change in elevation is going to be the same, or the head, right? Meaning your energy, right? Your energy change is going to be the same for all of these pipes, right? And that's why we can remember H. Remember H. I want to be very clear about what that H is. That H is not a distance. Remember, that is energy. This equation, when we write this equation, it's energy per unit weight, right? That's one of the first things we did. So that H is not actually a distance. It's actually your energy per unit weight, right? So basically, we are saying that my change in energy between my two reservoirs is going to be the same for each of these pipes. That's what we're saying, right? It's not an edge. I want to, and if you want, you can go back, look at the beginning, look at how we developed this equation from beginning, right? It's actually these each term in that frictional loss for your losses. It's actually energy per unit weight. Okay, I want you to remember that. Don't forget it. Okay, so let's move on. Let's look at another problem, and this is where actually we are going to end. Actually, no, I have two problems here that we're going to look at. Right? These are a little more involved. I don't want them to scare you, but I'm going to take my time and I'm going to break it down so you understand how we set up this type of problem, right? And then on Wednesday, we'll be in class again, and we're going to look at more examples, right? So we have two reservoirs here, right? But look at what's happening. The pipe between these two reservoirs, they're branching, right? They're branching off, right? Now remember, we said that Bernoulli's principle, we can apply it between any 2 points, right? So we want to analyze this problem, right? And you will get one of these problems for your exam. So you want to practice at least a couple of these problems. You will see a problem like this on your exam. I'm telling you now, right? So we have these two reservoirs, we're branching, right? So you see it starts off at B and then we branch at C to two branches, right? So then it says, look, two reservoirs have a difference of level of 6 meter, right? 6 meter, and are connected by a pipeline, which consists of a single 600 millimeter pipe, 3,000 meters long, right? So the first pipeline is 6 meters, 600 millimeter, right? That first pipeline is your pipeline that's going from B to C, right? It's 600 millimeter diameter. It's 3,000 meters long, feeding at a junction. So the junction is at C, right? Now I've drawn this for you, right? From this. The question doesn't actually draw, it gives you an image. So you have to be able to construct the reservoir and the pipelines and represent it from the language, right? But I have drawn it for you. Right. So it says that at this junction, the pipe, of course, it's a junction, so it splits, and you have two pipes now that are each 300 millimeter diameter. They're also each 3,000 meters long, and now they lead in parallel to the lower reservoir. So what does that mean? It means that now they are both, doesn't mean that they're running in parallel. It simply means that from where they start to where they end, right? They're starting and ending at the same place, right? Literally. And the head loss between those 2 points are going to be the same. That's what it means, right? And if F is 0.01, so they're saying, look, F is the same for all pipes, for every single pipe, for all 3 branches. They want to know what the total discharge is going to be, right? What is Q? Basically, they want to know what Q1 is, right? So how do we approach this problem? Okay, remember we said Bernoulli's principle, we can apply it to branches. So I am going to apply it to branch BCD. This internet is a bit slow, so I want it to expand, right? So We're going to apply it to branch B, this first branch, CD, this one. So basically, we're applying Bernoulli's principle between B and D, or basically, if you want, between A and F, these two reservoirs here, but I'm looking at branch BCD, right? So you see, that's why I write my first part in terms of A, then second part in terms of Z, in terms of F, sorry, right? But then now in this problem, I didn't tell you anything about entry and exit, about these points. I didn't say anything about the junction either, right? I didn't say anything about the junction, although you know at the junction you should have, it's actually still going from 6 to 600 because the branch is 300, 300, right? So then I'm looking at my losses, my frictional loss. This is BC, frictional, and then CD, right? And I'm also doing the same for branch BCE now. This branch, this second branch, BCE, right? Technically, those two branches are parallel because they're starting and ending between the same two reservoirs, right? That's why if you notice the first part of my Bernoulli equation, these two parts, you will notice they're between A and F, right? This is actually two parallel branches because they're starting and ending same 2 points, same two reservoirs, right? But what's going to be different is the friction, my energy loss parts, right? So here, my energy loss would be, of course, BC here, and then CE. All right, these are my pipe friction because I don't have any shock losses. So you notice I don't have any shock losses being represented here. So now I can simplify, right? You see where I'm simplifying. These are open to atmosphere. These are two reservoirs, VA and VF. Those should cancel out as well. There's 0. And the same thing here. So I end up with ZA minus ZF again, ZA minus ZF, and I end up with these two sets of equations here, equation 1 and equation 2, right? Equation 1 and equation 2, right? And you know what ZA and ZF is actually. They're actually the same, right? That's why I can write equation 1 and 2 equal to each other. So if you notice, I'm taking the first part here, which is equation 1, and putting it equal to equation 2. You can see that because they are equal, right? So now I can eliminate the expression with V1 inside of it, right? Yeah. But the problem tells you L2 and L3 are the same, right? Let me make this a little bigger. Now, these are in your notes, right? So you see L1 and L1, right? L1 and L3, the lengths are the same. They're all I think 3,000 meters, I think. Let me, here it's not. Hates it when it does that. No, it disappears. Don't worry, I'll get it back for you. Right? So L2 is equal to L3, D2 is equal to D3, V2 is also equal to V3. Why is V2 equal to V3?
Continuity principle.
Yes and no, but why?
Because we have the same height and the same diameter.
Yes, because the pipe is the remember this large pipe is splitting to two pipes that are basically the same length and the same diameter. Basically, these two diameter, D2 and D3, are the same. So the velocity will split equally. So V2 and V3 would be the same. Right? So I know that V2 will be equal to V3 because D1 is equal to D2 is equal to D3. This is why I'm writing this here. So again, some of these things you have to pay attention to that. This is common sense, right? Right? So if D2 is equal to D3, now I can apply continuity as well. It means that my D1 is equal to twice times D2, right? Or D1 is equal to twice times D3, right? Again, just need to take your time, all right? So now I can have, I'm applying my continuity again. Your Q1 is equal to Q2 plus Q3, but you know that Q2 is equal to Q3, of course, right? Because of this. And then I can go through and even simplify even further, right? This is my Q1 here is equal to Q2 plus equals Q1 is equal to Q2 plus Q3. This should be a plus, right? And I have my continuity principle, right? But remember, we know that V2 is equal to V3, right? That's why we can substitute here. We can substitute V2 in place of V3. So we end up with an expression, right? And we know that D1 is equals to twice times D2. And D1 is also equals to twice times D3. Right? And you know that D2 is equal to D3. So we can simplify and we can get expressions for V2 and V3. So V2 is twice times V1, V3 is twice times V1. Right? Because remember we said the diameter of the first pipe split equally now, right? And this is vital now, vital information now that will help us to work towards our Q1, our total discharge, right? We can work towards that total discharge, right? So I'm coming down again now, right? Or ZA minus ZF, right? So remember we right? Or ZA minus ZF. I'm just taking that equation, one of those equations from up here. This is I'm taking equation 2 and I'm bringing it down. This is equation 2. But we already figured out that V3 is 2 times V1, right? So we can substitute, we can remove V3 and put 2 times V1 in place of there and square it. And that's what we're doing right here. Right? So basically we are solving this equation to find V1. We need a value for V1. Right? I know it looks like it's a lot of taking your time and doing this thing. It's you have to be patient. It looks easy, but you have to take your time. Right? We know that ZA minus ZF is 6 meters. Right? I am just calling it Z. If you want, you could call it H, however you want to call it. Right? Here I just call it Z. Right? So if you want, you can use H instead. And I'm simplifying the entire expression, right? I'm going all the way down. I'm plugging in all my values here. You can see I plugged in my value here. 2 2s are 4. 4 4s are 16. But then I have a 0.5 below here because remember we said that D3 was a half of D1. Right? So now I can add everything. I can bring everything together. And now I have a value for V1, right? Remember, I'm calling ZH if you wanted to call it H, HGD1 on 18F L1, right? So I can plug in all my values. I know what H is. It was 6 meters. We know G. We know what D1 is. Right? The problem told you what D1 is. We know what F is. We know what L1 is. So we can find V. And once we have V, we know that Q is equal to A times V1. A times V. A1 V1. Right? And we can find the total discharge, which is Q1. Right? And now we have our value for Q. Right? Starts off very simple, huh? Right? But you have to do a lot of manipulation. And all you are doing here is using Bernoulli's principle, your knowledge on losses, continuity equation. That's all we've done here. We've not done anything different. Right? And paying attention to the geometry of your pipe system to work out this problem. You've not done anything, you've not learned anything new, right? Another thing you need to pay attention to is your reservoirs, your branches. So these two branches, they are considered parallel because they are between two reservoirs, and you are applying Bernoulli's principle to each branch, right? To each branch. I can't apply Bernoulli's principle to point B, C, D, and E all at once. I pick one branch, I apply Bernoulli's principle. I pick another branch, I apply Bernoulli's principle. And the reason why I can make this statement here, and I want to circle it in a different color, this statement here, where I'm saying equation 1, this is equation 1 here, and equation 2 are the same. It's because they are between the same reservoirs, right? They are between the same reservoir. Let's say I did this. Let's say I had something like this. And this is reservoir A, B, C. Right? Let's say I had something like that. Right? And I call this point 1, 2, 3, 4. Right? And I have branch, I'm going to call it branch A to 1 to 2 to 3. And then I have branch to 3 to B, let's say B, right? And then I have branch A to 1 to 2 to 4 to reservoir C. Right? Are these two branches parallel?
No.
No, they're not. Why?
Because
two different reservoirs. Oh,
they
Yeah.
are different.
They're not parallel. They're going between two different reservoirs. So basically, if you want your ZA minus ZB is not going to be equal to your ZA minus ZC, right? Because these two branches are not parallel. They're not going between your energy loss. Your head is not the same, right? Because they're going between two different branches, right? And that will take us to our next problem, right? So if we are going between two reservoirs, these can be parallel branches. Even if we split this thing, even if this pipe was to split into a third line, let's say you had a third branch off of this thing, off of it, those three branches would all be parallel because they're going between the same two reservoirs, right? But now that brings us to our last problem, right? Which is called a tree reservoir problem. Now, a tree reservoir problem is a little more complicated, right? And usually I like to solve this with using Excel, but I'll let you calculate by hand, right? So we are also going to look at a tree reservoir problem, right? And here I've set it up for you already, right? So we have this tree reservoir, right? We have reservoir A, B, and C. We have the branches. We have a pipe leaving reservoir A, and then it's splitting. But now one branch is going to one reservoir, and then the other branch is going to another reservoir, right? So the first branch is going to reservoir B, second branch is going to reservoir C, right? And we need to find, I think in this problem, we need to find the flow rate as well. We want to find Q, right? We want to find flow rate. So again, we're going between Z, A, and B. So I have the first one here. Now I've simplified it already because remember our PA and rho G and our PB and rho G, it'll cancel out. Our VA on 2G squared. VA squared on 2G will also cancel. Or VB on 2G would also cancel. So the only thing we're going to end up with is our ZA minus ZB, and we're only going to have our losses, frictional losses, because we're ignoring the losses at the entries and the exits, right? Where I've circled there in green, right? We're ignoring those. So I look at branch AB, the branch going between A and B, right? So we have the frictional loss in the first pipe here that I'm writing as this one, and then the frictional loss in the second branch, right? So the first branch and then this branch, right? And we do the same thing for AC now, right? And then we also use our continuity. So our continuity helps us to get a third equation, right? We know that A1V1 is equal to A2V2 plus A3V3. The problem told you that D1 is equal to D2 equal to D3. So you know that V2 is going to be equal to V3. You know that because those two pipes, the diameters are the same. So V2 must be equal to V3. Right? That's common sense. Right? So now we know that V1 is equal to V2 plus V3. Right? And the beauty about it is if V2 is equal to V3, it means that V1 is twice times V2, which is also to twice time V3, I think. No, let me don't do that. Let me not do that. Sorry, let me not do that. It's not. That's wrong. Let's work out the problem. Let's just leave it as that, as V2 is equal, V1 is equal to V2 plus V3. Let's just do that. Let's not jump to any conclusions here, right? So we set up our problem, right? We have our first two equations. This is equation 1, equation 2, right? Because we know what our ZA is 60 meters, ZB is 30, ZC is 15, right? And this is our datum down here. This is our datum. Right? So that's where we're getting this value, 60 minus 30, which is your ZA minus ZB. And this is your ZA minus ZC. All right. So you notice we are doing that. So we end up with three equations now. So I'm simplifying my equations above. And then our third equation is from continuity, right? So you see I have three equations now. And I'm just simplifying them. So I have 10.2, I took out the 10.2 outside, same three equations, I'm just simplifying, right? And I'm just simplifying, guys. That's all I'm doing here. I'm simplifying, right? I am simplifying. So I end up with an equation with V2 is equals to 2.94 minus V. So I get an expression for each one of my, how do we call it, velocities in terms of V1, right? So V2 and V3, I write them in terms of V1, right? And then what do? I then take an expression. Remember we said V1 is equal to V2 plus V3. So now I've taken, this is V2 here, you can see it right there. And this is V3. So we have an equation, a single equation in terms of V1 that I can use Excel to solve for V1. Because you can't solve that equation like that. You need to do what we call, we need to use a solver where we converge, right? We look at different values of V1 and we see where it changes, basically where we get an inflection point, where it goes, we substitute values of V1 into this equation and see when it goes from negative to positive. And where it goes from negative to positive, you know your solution is between those two answers, right? But this is best solved with Excel. So we solved it using Excel. In your test, I don't think I'm going to give you a tree reservoir problem. Before, I used to give students this to go and to solve it using Excel, where you set up all your equations and you get a single equation for V1 that you can then solve for V1. Because once you solve V1, then you come back and you plug it into your expression for V2 and your expression for V3. So you're able to get your velocities for the different sections of the pipe, right? And then you can come back and say, okay, since we have V1, V2, V3, we can find the flow rate for our total flow, right? This is one of the more complicated problems. And the reason I show students this is because in the real world, this is what you have to deal with. But a computer is going to solve this for you. You're not going to basically solve this by hand, right? Because you may have a pumping station or reservoir, and then you have 1,000 branches to all your different houses or whatever, and so on and so on. So you can calculate all the different flows and pressure drops and all that in the system, right? But we are not going to do this by hand. It's not designed to do it by hand. But if I do give you a problem like this, I can ask you to give me an expression for your velocity V1. So I can ask you to give me this. Or I can say, write all your velocities in terms of V1. Give me your V1, right? Give me V1. Give me an expression for your velocity, your V1. Right? Because this is basically an equation for V1. Right? And it basically, if you were to, you can actually plot it. And you get an equation for it that might look something like this. So where V1 goes to, where this expression goes to 0, right? So some value of V1, right? This is your V1 axis. There's some value that makes that 0. This entire equation 0, right? But again, I'm not going to test you on this to set up something like this, right? The most I might give you, and I doubt, I'm not going to test you on this, but I want you to still work a problem, right? Where you learn how to do we learn how to set up a tree reservoir problem, right? Again, we have not done anything different. All we have done here is applied Bernoulli's principle, losses, continuity. That's it. We've not done anything new, right? At all, right? So, having said that, let's look at some examples, right? I think I looked at this example already, but let's look at it again. Because what this example is asking you here is to find the value of K if we were to this expansion, we were to represent the loss as K times V1 squared on 2G, right? So again, this is plus losses, right? And we've been given all the unknowns, right? So we write our Bernoulli's principle as usual for point 1 and 2 plus the loss, right? Then we have our continuity equation, right? We've been given or P2 minus P1 on rho G. We've been told what that is, right? Which is 0.36, right? So we basically rewrite the entire expression where we have our P2 minus P1 on rho G, and we're basically solving for the value of K. That's all we're solving for. We want this coefficient, right? So we rearrange, we can find everything else. We know that Q1 is A1, V1, so we can use that continuity principle to find V1 and V2, right? Which we did up here, right? Based on the continuity principle. And then we can then plug that into our expression, right? For V1 and V2 to help us to find K. All right. Same thing we've done here, right? I think this problem also is asking us to find, I think, our value for I think Q, right? It's a little different from this one because now we are not taking this as K, but the thing I want you to look at is, you notice K is 0.49, right? So we've kind of theoretically worked out what the K value would be, our coefficient would be for an expansion. It's usually always a half, right? That's why we take it as a half, right? But here we're using it as a half already, right? Which is here, right? When we go from a small pipe to a large pipe, right? But what I want you to focus on, I know we're almost out of time. I want you to start looking. So on Wednesday, I'm going to come and we're going to start looking at just problems. We're just going to work problems, get you to set up problems, right? This part of setting up the problem is the biggest part, right? How you apply Bernoulli's principle to set up your equations in the beginning is the critical part of solving these problems, right? So as I said before, you will see a 2 reservoir problem on your exam. Be ready for that, right? If you do see a 3 reservoir problem, I'm not going to ask you to solve for V2 and V3 and all of that. I don't think you could try, but it's going to be a bit tricky, right? The most I'll ask you to do is to give me an expression for V1, or to give me an expression or to prove an expression for V1. I would say prove that V1 is equal to this, or I'll ask you for it. Or I might say, give me an expression for the flow rate for Q, right? So if that was the case, you would basically take this A1 V1, and basically you'd be pi D1 squared over 4 by this entire expression up here, by this V1 minus square root of 2.94, right? So basically you would say that Q1 was equal to pi D1 squared on 4, which is the area, and you write this entire expression here, V1 minus 2.94 V1, blah, 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 right? That's the most I'll ask you to do. I'm not going to ask you to solve this. Maybe for your own knowledge, we can do one on Wednesday where you actually use Excel. Have any of you used the Excel solver before?
Maybe once.
Right? So between now and Wednesday, what I want you to do, actually, I want you to use the Excel solver to solve this equation. Go on YouTube and use the Excel solver. Take this equation. You don't have to go set up the whole thing. Just take this expression here and look up how to use the Excel solver to find the solution to this equation. It's a very easy thing. It's you won't believe how easy it is, right? Just take this expression and use the solver to do it. Right? That's all. Now, what I want you to do is just type your name into Zoom, into notes. So if you're here, type your name into Zoom, and that is what I'm going to use for attendance. So I know that some of you are probably joining and you have some weird name, and I have some other classes I teach, and I tell students, please sign in with your full name. So as if I go in and I can use Canva, I can use Zoom to take attendance. And if I see someone with a different name, I don't know who it is. And then you get marked absent. And then I have people saying, but I was there. And then you have your name as Nigerian Shawarma. I don't know who that is, right? So please put your name, all right? Anyway, with this, we won't have any more Zoom lectures, but please just type your name into Zoom, and I'll put your attendance. But any other questions on this? Right, so your final exam is going to be next week, Monday. That's what they have. I would have set it for Wednesday, but that's what they came back with as a schedule, so I'm going to stick to the schedule, right? Your exam is mainly going to be on losses in pipes. But you realize that you cannot do these problems without using Bernoulli's principle, without using continuity, right? You may see a question on flow rate, right, on a pitot tube or a Venturi meter, and on losses, right? You would see a problem, maybe one or two on losses, another one on flow meters. Basically, what I said to you in this morning's email, right? I'm not going to test you on everything you did before, right? It's not a comprehensive test from what we did from day one, right? So you know what to focus on. So on Wednesday, we'll come and we'll just use it for practice problems. I suggest you start doing some of the problems that are on Canvas, so at least you can come if there's something you've run into a problem with, and I can help you if you're stuck and you can't, and you're not able to make any progress, right? But there are problems there with answers. Try them, but I'll come ready for us to look at some problems as well to help you prepare for your exam next week. If there's nothing for me, I will stop here. I wouldn't keep you any longer because I know we're already over time. And I shall see you on Wednesday. All right. Have a good night.